The webinar today will cover the training in Pdisp. So it will cover how Pdisp works, how to set up a file, and for people who are familiar with Pdisp, it's also going to cover tips and tricks in Pdisp. So for example, when you're putting in inputs, when you're getting outputs, how to run the analysis really swiftly and efficiently. So I didn't introduce myself as well. My name is Zina Farouk, so I'm our application specialist and I'm also a geotechnical engineer. So as I mentioned, we're going to introduce the method. We're going to go through a quick case study showing how Pdisp is used. We're going to set up an analysis from scratch in Pdisp and run it. And I'm going to go through the shortcuts and tips as well. So what is Pdisp? Pdisp calculates soil displacements due to pressure in 3 dimensions. It can be either loading or unloading. So it can be, for example, demolition and heave problems, as well as loading and surcharging on soil. You can predict also the settlement of flexible footings and rafts. So there are 3 main analysis methods that we incorporate in Pdisp. 2 of them, those methods are elastic analysis methods. They give you effectively immediate settlement. So those 2 methods are the Boussinesq method, which gives you stresses and displacements in the soil, and the Mindlin method, which gives you displacements only, but can also deal with shear. So if you've got a loading on the soil which has a lateral component, you might want to use the Mindlin method. So in terms of comparisons of the 2 elastic methods, the Mindlin is better if you've got some horizontal displacements that you want to calculate or traction forces. But the Boussinesq is better for soil nonlinearity and stress changes as well. So if you're interested in the stresses in the soil. So just a note on the 2 methods. For the Boussinesq method, which we're going to set up today and use, the number of displacement levels are pretty important. So if you don't have enough displacement levels in your soil, and when we get to that section, it'll become more apparent what that means. The calculation isn't as accurate. So try and put enough displacement levels. And this becomes pretty important if you have a lot of strata and they're closely spaced. If you've got very different Poisson's ratios as well, you might want to reconsider the Boussinesq method. And if there's sudden changes in stresses between the soil, you've got to check it quite carefully. The Mindlin method gives a horizontal movements, and it also gives you settlements above loads. So if you've got loads for some reason that are below the soil level, or you want to get settlements above the load for any reason, then the Mindlin method will give you better results. But all of this is covered in much more detail in the user manual. So the third method I mentioned is the consolidation method. So consolidation settlement occurs when you've got expulsion of water from the voids. It deals with variable soil permeability, so the rate of settlement can vary from one soil to another. So Pdisp will consider primary and secondary consolidation. Primary consolidation is where the volume change is due to reduction in pore water pressure. And the secondary consolidation generally kicks in when the degree of consolidation is at 95%. And this is where the volume change is due to the rearrangement of the soil particles at constant pore water pressure. So the instantaneous settlement in the drained and undrained soil is actually calculated using our elastic methods. It then applies primary consolidation for undrained soils, for example, in clays where you've got water. It applies either the MV method or the CC method. Again, more details given in our user manual about how these methods are applied. And in the long term, it applies a secondary consolidation in undrained soils. So just to help you visualize what's happening, we start off with this blue line, which is the elastic immediate settlement. You then have primary consolidation, which happens until the degree of consolidation is at 95%. And when that happens, you then get the secondary settlement kicking in. And the total settlement is an addition of all these values. So hopefully that helps you understand it, but if you need some more clarification, there is a webinar that covers this in much more detail. So in terms of the input in Pdisp, as I mentioned, it works in 3 dimensions, but you need to tell the program where you want to calculate displacements. So the user needs to put in either a grid, which will give you effectively settlement contours, a line, and that might apply, for example, if you're looking at an adjacent building and you want to model the line of that building, the external wall, for example, or It might be that, for example, you've got a utility or a tunnel and that represents a line and points as well. Loaded areas can be rectangles and circles. Pdisp also has a wizard that calculates a loaded area for a polygon. I mean, these polygons can be quite complex. And if you give Pdisp the x and y coordinates, it will calculate that load for you. So when we go into the program, it'll become a little bit more clear what's going on. The base is defined by a rigid boundary. The rigid boundary is generally, I would say, where you're hitting rock or you believe that no further settlements will be occurring. The ground is modeled as a series of vertical soil profiles. So this is the soil profile here, for example, where you've got different strata. And say you've got dipping strata or you've got a soil lens, you can then put them in soil zones. So this particular example here isn't necessarily quite realistic, but for example, you could have dipping soils coming down, and so you can utilize different soil zones to model that. And then you also need to specify which of those three analysis methods you would like to use. So just a note on soil zones, I did mention like you're effectively looking down now at your analysis. So this is the X and Y and the Z is going down. So these are how the soil zones work. The higher number of the soil zone overrides the lower number of the soil zone. And what this means is that you can have soil zones overlapping each other. And this is quite good if you've got, for example, a soil lens or a lens in your strata. In terms of inputs, again, I'm going to go through this when we actually set up the problem, but I thought it's nice to kind of, explain it before I go in. You can put defaults in the program. So if you're constantly, for example, interested in a horizontal orientation, if you generally have an angle of the load which is at 0 degrees, you can actually put this in the gray area, which is the default, and you can tab it, which will make things much quicker to set up the analysis. And we can edit those defaults as well. Another table tip, again, I'm going to use this when we set up the analysis, is that equal copies the cell above and equal equals copies the whole line above. And this feature is actually really handy when you're trying to set up grids and you're interested in setting up grids at different levels. If you right click on a table input, you can basically change or modify a whole load of values. This is coming pretty handy actually for a couple of users. I know, for example, they've got the e value wrong by a factor when they input it in, and you can just quickly right click and modify the whole line, for example. So that does really help. So in terms of case study, PDISP is used a lot in industry, but this case study I found was particularly interesting because it compares PDISP to 3D FE. So this is a case study from Arup, and they were responsible for designing a building in London directly above some LUL tunnels. So this was a really sensitive project. So 3D FE analysis using LS-DYNA modeled the building in piles, but LUL required a Category 2 check analysis to be done. And that was done using PDISP. And the results were really interesting there. So this is just a kind of snapshot of the graphical output just to give you an idea. So this is, for example, the lines, the displacement lines where you're calculating the displacements. And these lines would have been sitting along where maybe the crown of the LUL tunnels were. And it's showing the displacements along those lines. And it's also showing the displacement at the surface. So the surface is modeled here by a grid, and you can see the displaced shape. So this displaced shape is exaggerated because otherwise you wouldn't, if it's millimeters down and you're working in meters across, you wouldn't see the displaced shape per se. So in terms of stresses, interestingly, LS-DYNA and PDISP got identical stresses, which was really interesting to see. So PDISP does work very well, we know, in clays, and it compares very well. In this case, it really did. And also the maximum peak change in stress was matching for LS-DYNA and PDISP. And the displacement comparison was also very interesting. So the peak vertical ground movement in LS-DYNA was 3.18 mil, and the peak vertical movement in PDISP was 6 mil. And this is really what you would kind of expect because LS-DYNA is going to consider the structures and the stiffness of the structure and how that contributes, to reducing the vertical ground movements. But with Pdisp, it's giving you a conservative value, but it's not that far off Elastiner, which we thought was really interesting. So another thing I wanted to cover before I go into the program is recent developments. Pdisp is being developed constantly, and over the last 2 to 3 years, we've had a couple of features that I thought were worth mentioning. One is that people are creating increasingly large files. And complicated files. So multi-threading and multi-core processing is a feature that's been incorporated into PDIS to help it run much more quickly and deal with these, more difficult files. Um, Grid views and tabular output is a really great feature. I'm going to show you that today. So it really helps you kind of copy and paste results and put them into Excel much more quickly and easily. So I quite like that feature. Polygonal loading is another one I mentioned, and again, we will show you today. Consolidation settlement was also added quite recently. Unfortunately, I won't have time to cover that in this particular webinar, but I will try and link the consolidation settlement webinar and make that available to you in a resource page. Another development that's really interesting is that XDisp and PDisp can combine. So for those of you who are not aware, XDisp calculates ground movement due to excavations. But more helpfully than that, it calculates building and utility damage. So you could basically create a file in Pdisp, open it in Xdisp, and run a building and utility damage assessment. There's another webinar that covers how this is done and shows you how quickly it can be done, but it can be done with ease. That basically means now the functionality of Pdisp has increased because you can now do building and utility damage assessments with it. So I'm now going to go and set up an analysis. It's a pretty simple case, but I'll just show you how quick and easy it can be in a program like Pdisp. So we've got two sol profiles here, one with sol strata with a constant Young's modulus, and one with sol strata where the Young's modulus is slightly varying, and we've got two soil zones as well. So this soil profile will go for that soil zone, and that soil profile will go for that soil zone. So if I go to Pdisp, I've just opened up a brand new Pdisp file here. So I'm going to go to new. Right, so the Pdisp is separated into the gate. We've got the gateway here, and we've got the icons at the top, and we've got a standard toolbar at the top as well. So the Input Explorer is how you would start. So we'll start with the titles here. So, all these details will be output when you print either your tabular outputs or your graphical outputs, but I'm just going to say webinar example. And I'm going to put my initials in there as well. But it's really important that you populate this, especially if you're changing the file or using lots of different files together. The units, so we have a pretty international crowd today. I know you're all using different units, so this gives you different options for units, and it's better to try and set this before you start setting up the analysis. So look at the units first, please. I mentioned the analysis options. So the consolidation we're not going to tick on today. We're going to start with the elastic, and I mentioned that we're going to use a Boozanesque analysis and have a look at stresses as well. But here you might want to select the Mindlin. The global Poisson's ratio I'll leave at 0.2. The horizontal rigid boundary, if you remember, I mentioned this is where rock is at, or we expect no settlement to occur. So I'm going to put minus 30 for the rigid boundary. Okay, so that's fine. So now we need to input the sol profiles. So if I look at this here, I'm going to tab. So as you can see, the defaults are already up there. So the top level is 0. For the time being, I'll leave the number of intermediate displacement levels at 5. The Young's modulus at the top. So if I go back and have a look, the Young's modulus at the top was 20,000 kilonewton meters. So 20,000, 20,000, I put 200,000 here. And the Poisson's ratio I'm going to put as 0.25. I'm going to tab that. So I'm going to copy the line. Oh no, actually I'll just tab this one. I think that was -10 from what I remember. Again, I'll keep that. This was 40,000, 40,000, and I'm going to say equals here because it's the same value. And we've got the third layer as well. -20. I'll go for 60,000 here because I think that's what I remember it was. And Young's modulus.
Right. So last time when I left you, we had input in one soil profile. And we were going to input in another soil profile. So another feature that I wanted to show you, which is really helpful in Oasys Pdisp, is that you can copy and paste from Excel. And you might wonder specifically why this is helpful. The reason is that, like, for example, if you've got, if you're working on a site and you've got, you know, the same strata or similar strata, but you want to set up multiple files, I often find it useful for this feature. There were cases where, you know, we're working on a big program and generally the soil strata is quite similar, or a big project. So in that case, you know, you would use this particular feature. So I'm just going to copy and paste here from Excel. So if I go to soil profile 2, if I copy this, I can paste this in here. And there you can see I've got now soil profile 2, right? So I added the extra soil profile by using the tabs at the bottom of the table here. We're now going to go into the soil zones. So if I go back to here, the soil zone goes from a constant y, which is -100 to +100. Soil zone 1 goes from -100 to 0, and soil zone 2 goes from 0 to -100. So I think I can figure that out now. Right, so let's go -100, 0, -100, 100, soil profile 1, soil zone 2, 0, 100, and I'm going to use the equals again, and I'll put soil profile 2 here. So if you notice, I'm using constantly the 3D graphics view to make sure that I'm doing what I'm hoping to do. And this really does give you an idea that, you know, if you accidentally put the wrong X value or Y value in, you know, it'll help you immediately recognize the mistakes that you're making. So again, that's another top tip for when you're setting up your analysis. So we now need to go into inputting the loads. So if I look, these are the loads that I want to input. So 2 square loads with the centers given. The way Pdisp inputs rectangular loads is you need to input in the center and the widths and the lengths, and then a circular load as well. So if I go to Pdisp here, rectangular, right, so if I go for rectangular load 1, I'm going to work on the horizontal plane. First one was at 0.45. The level here is 0. So it's sitting on the surface. Width is 50. Length was 50. So this was a square. And the pressure that's applying on the surface is 60 kilonewtons per meter squared, and no tangential. Again, I'm going to tab through this. I'm going to say that I think this was at 10 minus 55, so it's a negative y. This is sitting a bit below the ground level. Again, the angle is 0. And the width for that, actually, it was not 59, was it? It was 50-50, so 50, 50, and this was 120 for the width. So this is a rectangle, so it's got a width and length, so it's not identical. And the pressure for this was a little bit higher, it was 70. Okay, so now again we can look in this, and yes, it's set up as we would expect. So it's great to have that in the background, so you can see. So I'm going to input the circular load now. So can I tab? It's a horizontal load. It's not tangential. And if it was tangential, I should really be considering using the Midland method. So 0, minus 5, minus, can't remember what it was actually. I need to check. 0, I know the radius was 45. So let me just have a look at the image and see before. 0, minus 5. Okay, so yes, the level is -1 as well. And the number of rectangles is how many rectangles you break that circle into, because it doesn't model a circle as a circle, it breaks it into rectangles. So I'll put a few more just to make it more accurate. And the pressure is going to be 50 kilonewtons per meter squared. And again, it's not tangential in terms of pressure. Okay, so let's just check this and see. Right, so that's sitting nicely. That's working as I would expect. Just going to give it a rotation round and a little bit. See? Right, okay, that seems to be working well. So fine, we've given it the actual, values of the soil profiles, and we've given it the loads, but Pdisp doesn't know where to calculate the displacement. So we now need to input in the displacement data. So just for an example, I'm going to put a point in. So it just gives you an idea of a displacement at a specific point. I'll just keep this as 0, 0. I'll say yes for calculation and yes for detailed results. The reason you might want to switch on and off calculations and detailed results is that if you've got a huge number of displacement points, lines, or grids, if you start calculating everything and putting detailed results for everything, what will then happen is that you will have a huge amount of calculation, and that will increase the calculation time. So just be aware of that. So let's put some lines in. So let me have a look and see what I had specified in my presentation. So as you can see, we've got the loads here. I've got a line going from minus, so let me see, so that's minus 70, minus 80 to 880, and minus 70, 75 to 40, minus 80. And so I'll have a look at that and see, and then put the grid in. So let's go in here. So displacement line, again, I'm using the defaults above. Minus 70, minus 80, and the Z level is 0, so these are at the surface. And it went to 880 from what I remember, and again, zeros. The Z level is 0 at the surface. Intervals, I will keep at 10, and we will talk about this in a bit. I'm going to put yes for calculate, so instead of changing it here, I'm going to change it in the defaults, so that in future, this becomes more easy, because I'm going to go for that for the next line. Let's go for displacement line 2. And that went from minus 70, 75. So that was started up higher up, again at 0. And it went to 40, minus 80. Again, 0, I'll copy that interval, and see now I can tab through and it's a bit simpler. Yeah, so I've got those two displacement lines in there. Yeah, and if I look at my graphical input view as well, I can see those displacement lines. So the green is the soil zones. I've got my loads working, and the displacement lines are across. Yeah. So now we need a displacement grid. The reason displacement grids are really handy is because they give you your settlement contours, and they're obviously very useful then for viewing your problem graphically. So I want to input this specific grid that I'm showing here. There is worth an explanation as well about how grids work. So with the number of intervals along and across the problem, you want to make sure that your grid points sit within your loads as well. And the reason is that, for example, if I had a very, very loose grid, I wouldn't be getting enough grid point calculations within the load, which means that I might be hugely underestimating where the load is. And when we go into this analysis, I'll show you ways that you can refine grids as well. So the way you input in a grid is it gives you two options. You either have a global X option or a global Y option. What this basically means is that if I had a global X option, I draw a line going up, and then I extrude it along the X direction. If I have a global Y option, I draw the line across here and I extrude it along the Y direction. So the length of extrusion is 170 meters, and this is the line that I'm extruding. So it's basically taking this red line and sweeping it up. So I'm going to input this in, and then I think hopefully that'll help you understand what I'm trying to say. So if I go to grids here, I'm going to put the displacement grid in. And I'm going to go for the global Y because that's what I put in, not the global Z. A global Z is if you wanted a grid going right down, so right down towards the Z direction. So that might be quite interesting if you're trying to maybe model a wall and the displacement that's sitting on that particular wall. So global Y. So I think my line, so this is the red line. I'm putting the start and end point of that red line. So my line started at -80. -90 and 0, and then it went on to 80, 80 in the X. The Y changes, it stayed the same, so the Y is still at -90 and 0. Okay, so I'm just going to keep to 10 intervals right now. The extrusion direction, if you remember, so I'm just going to go back to this picture just to help you. So this is the line I've just drawn. The extrusion direction was up there and it was 170 meters. Yeah. So the extrusion distance is 170. Intervals again the same. And I do want this to be calculated. And I do want detailed results, I think. Right. So now for one of the shortcuts. So if I type in here equals, I copy the whole displacement grid above. And you might be wondering, why would I want to do that? Well, if I call this grid 2, I just need to now change the Z value. So if I change this to -3, I can have a look at what's happening and get the settlements for the grid below the surface as well. So I have a surface grid and I have a grid which sits 3 meters below that. And if I have a look either in plan, you can see the grid now sitting nicely, but in 3D you can see that even better. Yeah, so you can see those two grids sitting on top of each other nicely. Okay, so I think we're ready to do an analysis. So we've gone through the imports, we've gone through the shortcuts, we've gone through the way the gateway works with the Input Explorer. So it's now time to run the analysis. Sorry, excuse me. So the analysis you can run by going to Analyze here. I should also save this as a point of good practice. So if I go to Save As, I'm going to save this as Pdisp 2. Always before we run an analysis, we generally try to save, just in case it takes a long time to run. Interesting here is it gives you a results comparison as well. So the maximum displacement difference between the Booz-Ness method, it gives the two values. So you can see it's marginal. It's around 1 millimeter difference. And it also shows you where this maximum difference occurs. So this is connected to the two methodologies as well. So it's quite interesting to see where it is. And if for any reason your Booz-Ness method and Midland method are giving you very different results, that's worth looking into to understand why that might be. Right, so that's now run. So let's go through the Output Explorer and see what's available to us. So you can check all your inputs here. In the Output Explorer. You can also have a look at all input data and results in one whole text output, but you can break down your results as well. So for example, I might be interested in what's going on specifically at the displacement line. So I've gone right down here through the text and I'm going to look at the displacement line outputs. So the delta Z, the stresses are all given here, and you can go, we're not showing consolidation results here, so we're not going to really pick that, but immediate is all we're interested in. But we can have a look at the different displacement lines, or we can have a look at all of them together, right? Another thing that you can do is you can export this table. So there are two options for export. One is that you can export a CSV. You might be wanting to copy it into a master spreadsheet, compare results with different areas, send this out in a different form. So you can go to export and it gives you the opposite option to put a CSV in. Another feature that I find really handy when comparing results is the grid view. So if I go to grid view now, I can easily copy and paste. So I can copy this and I can easily quickly paste it into Excel, maybe do a quick comparative analysis or save data that way as well. So I find that as a really helpful feature. Right, so now let's have a look at the results in Plan. So if you remember, we had the grids and the two lines here. I would like to have a look at the contours. I'm going to click on the fill in contours and have a look at what's happening at the surface. You can see where the two loads overlap. We've got a larger settlement, which is what you would expect. You can also have a look. This is what's happening at the surface, and this is what's happening when you go a little bit further down. So you can compare the two grids. If I want, I can annotate a value. So say I'm looking at a specific area. I'm really interested in what happens maybe near the center of the problem. It's giving me a settlement of 32.55. So that's also quite handy. Another feature that's worth noting, so if you have a lot of CAD drawings and you want to overlay these settlements on the CAD drawings, you can actually export the CSV results file and export the contours. So it gives you a number of options. So I can export the contours for grid 1, the Z displacements, and I can edit the contour values. I can change the intervals and do that. So that's worth noting as well. So those are a couple of things from the plan output. Another thing that's worth mentioning that I should say for checking is the soil column displacement. So a lot of people aren't really aware of this, but if you click on soil column displacement, and I'm just going to look at the center of the problem, the soil column displacement gives you the settlement as you go down the soil strata. And in this soil strata, you can see, the settlement is reasonably constant. But it might be that, for example, maybe you made a mistake in one of your inputs. You've put the wrong Young's modulus in, for example, for one of the soils. It'll immediately show in the soil column displacements. So it's worthwhile having a look at the soil column displacements as well. Displacement lines are another thing that we input. So if you remember in Plan, we said that we wanted at the surface the displacements to be calculated along these two lines. From the Output Explorer, we can click on the settlement for those displacement lines and quickly pick that up. So if you have a look here, you can see that basically I'm picking up the values along the displacement line, and I'm also picking up the horizontal and X displacement ordinates. So what this means is that you can choose a cursor tooltip and you have lots of different options to basically pick up your maximum values. I find coordinates of the nearest points quite useful. So if I click on this now, I can find that the displacement is a certain value near a certain point. So instead of having to look at the table and refer back to the table, I can find the displacements there. Another thing, if you right click, is that you can export this curve and you can save the image. So if you wanted to quickly put this in a report, you can do that. So right-clicking on the charts are really handy. And you can quickly toggle through the charts by going through this here. Yeah. Cross-sections here. So we've got the cross-sections. Sorry, something went wrong with my microphone there. So, so we've gone through the plan. We've gone through the cross-section here. The 3D graphics is another one that I just want to show you quickly. Yeah. So if I right-click and go to Wizard, you can look at the displacement results here. So if I go to displacements, I can have a look at the contours in 3D. Yeah, so you can have a look at that there. Interestingly, only one of our loads are sitting at the surface, so some of the loads are sitting underneath, and it's worth mentioning for the Boussinesq results, you're not going to see all the displacements from the top. So if I look at the stress results here, we're only showing some of the stress results, not all of them, because those loads that were sitting below are not considered by the Boussinesq method. So this is really worth noting, which is why you probably need a couple more displacement lines here. But one last thing I wanted to note before we go on and discuss things like polygonal loads is you might have noticed that even in the settlements, it's a very jagged result here. So, we're getting a lot of different results. We could possibly get a larger result around here. And the reason for that is that if you look at what's happening, we don't have enough intermediate displacement points either on the grid or the lines. So for example, we're only picking up a few points, only 1 point here when we could pick up many more. So what I would suggest we do here is we stop this analysis and have a look at what happens if we refine our grids and we refine our points. And this is really important for you when you're looking at outputs. Okay. So if I go to Internet Explorer here, if I go to Input Explorer, I'm going to look at the lines and I'm going to increase the intervals here. So I'm going to increase this to 40 and 40. And I'm also going to refine the grid as well. Say 40 for all of them. So let's see what happens, and let's see what happens also to the maximum values, because I suspect these values are going to change. Okay, so if I go to Output Explorer now, if I look in Plan and I show the results, you can see that actually it's increased the maximum value even in our settlements here. So we're getting peaks in value. You can see also a little bit more of the difference that you're getting between the two soil zones. If I look at the settlement, can you see that it's much more refined now and we can see the maximum settlement more clearly? So this is really a watch it, and it's very important in Pdisp that when you look in Plan at your results, that you're picking up enough displacement points within key areas. And if for any reason you feel that you can't cover a huge grid, say it's going to take too long to analyze, what you should be doing is you should be trying to create refined grids which are smaller around the areas of interest. So I'm going to show you how to do that now with a polygonal load. So I'm going to add a polygonal load. So say, for example, I've got extra information about a new load. So I'm going to go and add the polygonal load. So I'm going to tab at this, and the polygonal load is going to be at the surface. But I'm going to add now some new X and Y values. So one thing I find very useful about this is that by being able to add the X and Y values, what you can do is you can basically import much more complex loading from CAD drawings. So you just need the X and Y coordinates. So I've copied and pasted again from Excel. I'm just going to add a reasonably simple polygonal loading, but the interesting thing to look at here is the display. So this is this display with the larger loads, but you can actually change tolerances to change how this is considered here. Yeah. So I'm going to increase the tolerance a little bit to model this load a little bit better. Right. So that polygonal load is now in there, but I also want a grid around that polygonal load, which gives me much more detail. So another feature that I haven't really touched upon, it is covered much better in some other webinars, is the graphical input feature. So if I go to the Input Explorer and Graphical Input, you can input in soil zones, displacement lines, and points and grids here. So for example, if you found the whole process of inputting a grid a little bit difficult, this really is much easier. So I'm going to go to Displacement Grids. I'm going to click on that. And in the Graphical Input option, I'm going to input in a grid here. And I'm going to make this quite a fine grid, so I really do pick up on a lot of points. So the level was 0 because that's where our surface load is, and I'll say 50 and 50. Okay. Right, so that's a really refined grid now. So shall we run this analysis and have a look at what we're getting out? So again, just because I really do like this feature, it's graphical input, double click on it, and you can input the grids in this way, but a line could also be input. So if I wanted to put a quick line to just have a look at what's coming across there, you could do that. So let's have an analyze and see. So as you can see, it's taking a little bit longer to analyze now because we've just got so many points. So at this point, you might want to have switched off the other grids to just make it a little bit quicker. Okay, right, so let's have a look at our outputs now. So if I look in plan, I'm going to toggle through the grids. So we've already seen the results of these two grids. But as you can see now, I've got the results of this grid here. I have not inputted in properly. So immediately I can see that I've not done something. So if I look now at my polygonal load, inputs, loads, polygonal, I did not give it a value of load. So this is a really good example through my mistake to show you how to input things in and check your results. So again, sorry, bear with me. I'm going to say OK. And now again, we're going to have a look at this plan and check our contours. So I'm going to look and toggle through. There you go. You can see really clearly now a very refined grid for that. And if I wanted to now look at this in 3D, I can see the surface loads. If you remember, I showed you the wizard very briefly, but what I'm going to do is I want to show you the 3D settings wizard because this is really a very useful feature for clients and putting reports in. So I, for example, show the displacement results. I might want to only show the results maybe for the grids and lines. So I'll click off the points, and maybe I only want to show the results for displacement grid 1 and 3. Okay, so you can also have a look at, for example, I've got the fill contour here, so I can apply that and have a look at what's coming out there. The loads are interfering, so I'll show the loads as arrows. I'll apply that, and I can see much better what's going on there. And then I might want to refine my contours, so I can change the intervals here. Change that to 5 mil, apply that and have a look and see. Yeah, so that's becoming much, much clearer now as to what's going on. Some people are interested in showing deflected shape. I mean, this is just generally to show people where the maximum movement is or to quickly see where the maximum movement is. Like that. I can see the maximum movement here as well. So you can see that much more movement is occurring here because of that polygonal load. So if I say OK, I can have a look at the deflected shape here. So there are a number of options with Pdisp to quickly pick out where you're making errors, where maximum movements might be, refining displacement results and having a look at things. I mean, I went through things very quickly, and this is how, as an engineer, if I was analyzing something, I would be examining a file. So, I hope I covered everything properly, and I hope you appreciate the kind of tips and tricks that I've showed you. But now we've set up the analysis, I think it's time to summarize our features and go through what we've done and then consolidate our learning. So I input in that value and I've shown you a number of tips and tricks that I wanted to go through and summarize. So again, with the input entry, the equals and the equals is really helpful. Copy and pasting from Excel is a useful feature, especially if you're working on a site or you're sharing analysis with colleagues. Grid and line entry, so graphical input for quick grid entry was a really useful feature, and I showed that to you today. Consider the number of intervals really carefully. So when you're inputting a grid or a line, if you don't have enough points or if you're not picking up key areas, you could not be picking up your maximum displacements, which is what actually happened when we initially set up this analysis today. The polygonal load wizard is a really handy feature, and you can import load coordinates from Excel or CAD. In terms of outputs, I showed you different options for graphical plans and wizards, tabular exports to Excel, and also the graphical grid view. So for example, if you remember, I right-clicked when we looked at the tabular outputs, and I can quickly copy and paste values that were important to me. Right, so using Pdisp from home. I know a lot of you who have joined me today are working from home, and we just wanted to help you with that because we've had a lot of queries come up about that. So one is that you should run the analysis file locally. So wherever possible, save the file on your C drive, copy it from the network, and then copy it back onto the network. Another one is the backup feature. Please go to Tools and Preferences, and you can make sure that the file is backed up regularly. Are you using the most recent build? Because, you know, this, as I mentioned, the software is developed quite heavily. We do a lot of fixes. So could you check that you're using the most recent build, and also managing your licenses. So this doesn't apply to a lot of our users, but if you are using a network license specifically, sometimes you might find that you can't access the software, and therefore you can use the license portal. So if you're using a network license, use the license portal. Another thing is training and support. So, you know, we are there for you in terms of training courses. We often run them both in-house in offices, online, and on a one-to-one basis. But there are a lot of other features that are available for you as a customer, absolutely free. One is a tutorial manual. It's a step-by-step guide on how to set up a number of things. There are some features I couldn't cover here today, for example, like nonlinear soils. That's available in the tutorial manual, so have a look at that. The user manual gives you so much more detail about the theory itself. So again, there were things that I couldn't really cover in detail, like the consolidation method, or, you know, the detailed method of how Boussinesq and Midland work. That's all available in the user manual. Online, in our support section, we have tutorial videos, and previous webinars cover consolidation, polygonal loading, and the Pdisp and Xdisp connection. So how Pdisp can be used to calculate building and utility damage assessments. If you're having any difficulty with the files that you've set up or the analysis you're doing, email us. Please do, because, you know, we can help you. We can check what's going on. The only tip I would have if you're emailing in support is send us your analysis file and any images of specific areas that you find, you know, you have questions about. And again, I did mention at the start that we run training sessions. So if you need that, please let us know. So I've covered quite a lot today. I went through it really quickly. So thank you very much for your patience. And I'm sorry if you were disconnected for any reason. There was a problem with GoToWebinar, but I hope that whoever was able to join really enjoyed the second part of the webinar. So I introduced the methodology in Pdisp today. I talked about a case study which compared Pdisp to 3DFE. I set up an analysis, I ran it, and I went through kind of tips and tricks as to how you would use the software most efficiently. So I hope that was all very helpful. And it would be great now if you could type in the questions box any questions that you might have following the webinar we've run, and I'll answer all those questions live.